Okay, it's an enormous pleasure for me to introduce today's colloquium speaker, Mike Manfra. Mike is the Bill and E. O'Brien Distinguished Professor of Physics and Astronomy at Purdue. He's also Professor of Electrical and Computer Engineering, Professor of Materials Engineering, and Scientific Director of the Microsoft Quantum Lab in West Lafayette. Mike started his career, the first 10 years at Bell Labs, and he's been at Purdue since then. He's an outstanding condensed matter physicist, but also a brilliant materials engineer, and both of these came together in the work that he's going to talk about today. Those of you who are younger than me, which is most people here, don't remember this halcyon period when the fractional quantum Hall effect was discovered in 1982, and then 1 year later, presumably through divine inspiration, Bob Laughlin solved the problem. But there was a very deep and important part of that solution, the existence of quasi-particles with fractional charge and fractional statistics, which is implied by the theory. So I think nobody sensible has doubted the existence of these excitations. But although there were attempts, many attempts, to observe them convincingly and directly in experiment, it's only in the last few years that the work that Mike will tell us about that this important central piece of physics has been observed convincingly. So that's enough introduction.
Okay, thanks a lot, Steve. I appreciate the warm welcome. Yeah, and it's great to be here at Stanford. I was thinking I've had a lot of friends and collaborators on the faculty over many years, and yeah, it's really great to be here and tell you this story. But in preparation for it, I was thinking over this past weekend of all the people I know who are now high-flying faculty on the Stanford campus, and how these people I knew at various stages of life, and I'd like to review a little of that for you, and how my professional career is always trying to catch up to these people and see whether I can match up to all these great people at Stanford. So I'm going to take you back to a place called Winthrop House. When I was in college, I lived in this brick building dormitory, and this was in Cambridge, Mass, 32 Mill Street, and once you are placed in one of these houses, you spend your upperclassmen years, all 3 years, living in the same community with the same people, so you get to know them fairly well. And I'm going to put up some pictures, some grainy old pictures, and see if you can guess who your colleague is here. I don't know if Mark is here, but it's Mark Schnitzer. Okay, 1992. Another person. Eva. 1992. Now, it wouldn't be fair to embarrass them with these old grainy pictures. There's me. I was also there. I had more hair, and it was a different color back then.
We're trying to catch up to you.
Yeah, okay. And so, you know, I was in the company of some really great physicists even back when I was a kid. And, you know, you try to do your best to keep up. Now, there was one other member of our house back then. He's not a physicist, but from what I hear, he's been modestly successful at Stanford over the years. So my next door neighbor was called Diceroth he lived next door to me for a couple of years. So these people were all in Winthrop House in the early 90s, and I've been trying my best to keep up with them, and now they're all super successful people here at Stanford. And it doesn't end there. I went on. I did my PhD at Boston, and then after that, I was feeling pretty good. I went down and I was offered a job as a postdoc at Bell Laboratories. And, you know, I thought, okay, I'm doing okay. I'm going to be a postdoc at Bell Labs. But that's when I met Harold Huang. And so I went down to Murray Hill, New Jersey. I met Harold. Harold was 16 years old at the time and evidently had been a member of technical staff for 3 years already. And so he informed me that I better get to work and work really hard if I hope to join their ranks. So most of my professional career has been trying to keep up with all these great people at Stanford now. So hope you enjoyed that. Now what I'm going to really talk about is quantum statistics and the journey that we had to go on and to prove some of these most profound or demonstrate some of these profound aspects of our understanding of topological phases in reduced dimensions. And since this is a colloquium, not everyone's an expert. It's for students. I just thought I'd take it very simply and start out with our basic notions from quantum mechanics. So, and it has to do with quantum mechanics and the notion of indistinguishable particles. So in quantum mechanics, if we have a multi-particle system, we can write down the wave function here, and we can write it as a function of the many coordinates of the particles, labeled here x1 through xn. And that tells us what we can know about that, and the Hamiltonian tells us what we can know about the system. But we have this notion of indistinguishability that, electrons are all the same. They don't have different color hair or different pitch to their voice. And so this indistinguishability has consequences in quantum mechanics. And for just a simple example, we can consider two identical particles in one dimension. And by identical, I just mean that they can't be distinguished by any internal quantum numbers. And so for a two-particle wave function, where we have labeled by the two positional variables x1 and x2, we know that the square of the amplitude tells us the probability of finding particles at position 1 and position 2. And this only makes sense if that amplitude squared is the same if we exchange the position of the two particles. It can't matter since they're indistinguishable, the probability. So this implies that the wave function is the same under interchange up to a phase factor. Okay? Now, if we get a little bit more formal about it, we say we introduce an exchange operator, px, where we act on the two-particle wave function that flips the position of x1 and x2. Well, if we do it twice, we square that operator. We know it's the identity. We flipped it once, we flipped it twice, we bring it back to itself. So that implies that the phase factor e to the 2i alpha has to be 1, or that this angle has to be 0 or pi. And so for wave functions that are symmetric under particle exchange, they're bosons. We call them bosons. And if under exchange, we pick up the minus sign, they're fermions. And we know that whether they're fermionic or bosonic has profound implications on how these particles behave in the aggregate. There's a lot of differences between the behavior in ensembles of bosons and fermions. And so let's just push that a little bit further. We also know that from the early days of quantum mechanics that spin and statistics are intimately related. And so we categorize particles as being fundamental particles as either being fermions or bosons. And we know that there's a connection between the spin of the particle and whether it's a fermion or a boson. So particles with half-integer spin are described by fermionic wave functions, antisymmetric under particle exchange. Particles with integer spin are described by bosonic wave functions, and symmetric under exchange. And we know that this has profound differences. If all you need to know to explain a lot of the properties of solids is that the electrons are fermions, they obey the Pauli exclusion principle, they can't all be in the same quantum state at the same time. That and a little bit of symmetry, crystal symmetry, goes a long way towards explaining why some materials are metals, some are insulators, and some are semiconductors. Conversely, if we have bosons, they are social creatures. They like to flock together. We can have Bose-Einstein condensation of a certain atomic species. And this laser pointer I have, lasing, is possible because of the bosonic statistics of photons. So bosons and fermions behave quite differently, and quantum statistics has a profound impact on the properties that we see. Now, starting in the late 70s and going into the early 80s, theorists started thinking, well, is that all there is? And as far as we know, I think, that's what we have in 3+1 dimensions, or fermions and bosons for fundamental particles. But going back to like the late 70s, some mathematical physicists were thinking about, well, what if we restrict our physical systems to reduced dimensional systems that are only operating in 2 dimensions or perhaps 1 dimension? Is everything the same there? And it turns out the answer is no, things can be different. And what I would call sort of the birth of this idea that you could have fractional statistics, others can correct me if I don't have the references right, but in 1982, Frank Wilczek considered the quantum mechanics of a composite particle, a charge tied to a vortex, basically a composite particle comprised of a charged particle and a vortex acting in a 2+1 dimensional space. And he just worked through the basic quantum mechanics of it. And he found that the spin of these composite objects could be fractional. And like the spin, so could their statistics. So this is where we get the term anyon. I think it was just a joke that they can have any statistics or any spin. And so the statistics of these objects, like their spin, interpolates between the usual boson and fermions. And there's a great parenthetical statement that always looks interesting in hindsight. Although practical applications of these phenomena seem remote, I think they have considerable methodological interest and shed some light on the fundamental spin statistics relationship. Now look at the date, 1982. Stormer, Sui, and Gossert reported the fractional quantum Hall effect in the late 81. Bob Laughlin explained it not long after. And that explanation relied on the state being an incompressible quantum liquid that had fractionally charged quasi-particle excitation. So the fundamental explanation of where this phenomenon came about necessarily came with fractionally charged quasi-particles. Now, there's a lot of activity in these early days. Bert Halpern and then others were extending this and trying to build out that there was a bunch of fractional quantum Hall states being observed, and how do you go from the Laughlin series to these hierarchical states. And what Bert noticed is in trying to work through this hierarchy that in addition to the fractional charge, these excitations must have fractional statistics as well. So there's this statement, the appearance of fractional statistics in the present case, very Bert-like, very, matter of fact, strongly reminiscent of the fractional statistics introduced by Wilczek to describe charged particles tied to magnetic flux tubes. Now in hindsight, 40 years later, of course, we all know that that's a good model to be considering what's going on in the fractional quantum Hall regime of charged particles tied to flux tubes or vortices in the wave function. Less than in the same year, or essentially the same year, Wilczek and collaborators Schrieffer and Arovas put this on more theoretical ground. This is a paper I think all graduate students should read. It's a PRL. It's a page and a half at most, and you don't have to know anything about conformal field theory or anything like that. It's just basically calculating the Berry phase, and you can follow along. And so by 1984, this phenomenology of the fractional quantum Hall effect that I'll tell you about has been put on firm theoretical ground by Laughlin and subsequent work. But it has some very unique properties. Fractional charge, meaning sharp quantum number, that's a fraction of the electron charge, and fractional statistics. And the question is, okay, if you can take the viewpoint, well, we have a quantized Hall plateau, so therefore this must be true. It's one way. You could also say, well, how can I probe those properties directly? And that turns out to be a more subtle and tricky problem. That's the sort of the story I hope to tell you about now. So again, just to put this in context for students, we know the world of elementary particles. We have fermions and bosons. They have quite different statistics and they behave differently. And all the fundamental particles you know and love fall in these categories. But we have these emergent degrees of freedom, or if you want to call them particles, in low dimensional systems that can act as anyons with sort of unprecedented properties. They can have fractional charge and fractional statistics. And what I mean by that is, these are sharp quantum numbers. They're not like kinda E over 3. The charge is really E over 3, and the statistical angle of these Laughlin states is a well-defined angle. And so they're properties that are suspected or known to be properties of these fractional quantum Hall effect states, but they're very different from our notion of other systems. And there's anyons come in all kinds of flavors. The ones I'll talk about are not known as abelian anyons. There's also other theories that give rise to non-abelian anyons, so that these actual operations of exchanging particles don't commute, and that's where they actually correspond to having a degenerate manifold, and the change of exchange rotates within that degenerate manifold, and that's where a lot of the interest in comes about, because it's potentially useful for quantum information processing. You can store information that way. I'm going to stick to physics and the abelian cases here, but there's a whole bunch of anyons that we now know may be found in nature, and I'm just going to show you the simplest case so far. So, and again, to put this in context, I'm going to talk about the best developed and mature topological system that we know of, the fractional quantum Hall effect, specifically in gallium arsenide, but that it's not specific to the concepts are not specific. There are many condensed matter systems where we expect to find anyons, quantum spin liquids, topological superconductors, both intrinsic ones and manufacturer or engineer ones I work on as well. All the great stuff that's happening in the 2D materials, such as a quantum anomalous Hall effect. This is some data out of MIT. It looks like Sormer and Sui's data from the early 80s, where you have quantization, only there's no magnetic field. There's no 13 Tesla magnetic field applied. So there's, this is a very active area, and lots of systems may be supporting anyons. So hopefully for students, that's interesting. What I'm showing you is, I hope, a template on a fairly well-developed system where we can actually probe these properties and think about how to study them and manipulate them. Okay, so I haven't talked about what the fractional quantum Hall effect is. We have the world's expert in the audience. There are lots of people who know more about this than I do here, but I just want to show you the basic phenomenology of what it looks like in a modern sample. So I take a layer of gallium arsenide, a low band gap semiconductor, and I put that layer in between two layers of high band gap semiconductor, say aluminum gallium arsenide. That forms a quantum well. The electrons are confined to about a 30 nanometer wide quantum well. At low temperatures, the motion in the z direction is quantized. It's only in the lowest electric subband. It's essentially a two-dimensional electron system. And over many, many years, the work of many people, material scientists, we've gotten better and better at making these heterostructures and using a technique called molecular beam epitaxy. And so we made them purer and purer and had good ideas about how to make the heterostructures. So if you look at the transport properties, and I'm going to tell you about transport properties here, are very simple. I just take a square or a rectangle of material and I slap some ohmic contacts on. And I drive current in a particular direction, and I monitor the resistance or the voltage drop along the length of the sample, and I monitor the voltage that builds up across this sample. That's called the Hall voltage. And I cool this sample down into a dilution refrigerator. I get it around 50 millikelvin or so, and I apply a perpendicular magnetic field, and I look at what these transport coefficients look like. And classically, the blue line here is the Hall voltage, or the Hall resistance. And classically, you know that the Hall voltage should be just a straight line. It's proportional to magnetic field, inversely proportional to the density of carriers. And you see in this data the remnant of that linear background. But you also see some very sharp flat features, these plateaus that I'll talk about in a minute, that interrupt that behavior. Then we also monitor the resistance along the length of the sample. And classically, the magnetoresistance should be, there should be no classical magnetoresistance. It shouldn't matter. But what you actually see is this sort of spiky behavior where most of the time the resistance is zero. It's not a superconductor. There's no dissipation, but there's a Hall voltage. And then it's interrupted by these spikes of resistance. Those are the insulating states that when we're making transitions between the various quantum Hall states. And so you see these plateaus. The most prominent one here is nu equals 1, where we have a broad 0 in resistance and a flat plateau in the the Hall resistance. And you see this number 1 associated with that. That's called the filling factor. It's a ratio of the density of electrons to the number of states available in the Landau level. When I quantum mechanically apply a magnetic field, the spectrum breaks up into Landau levels. When the degeneracy of the Landau level meets the density of electrons such that I have a 1-to-1 correspondence, that's filling factor 1. That's where I see this phenomenology of quantized Hall plateau. And the miracle of the quantum Hall effect is that it's so precisely quantized to h over e squared to, I don't know how many digits now, 10 decimal places or something now. And this is in a macroscopic sample, ugly looking sample, and that quantization is what was so remarkable. Now, these integer states are just kind of boring in hindsight. They're when the chemical potential lives in the gap between Landau levels, the single particle density of states. But we see the same phenomenology at these other filling factors that have fractional value, 2/3, 3/5. And even though the phenomenology looks the same, a quantized plateau and a 0 resistance, what drives it is quite different. And that was explained to us by Professor Laughlin. So in modern samples, you know, you can go to town doing wiggleology and studying all these little fractional states that develop, if you're into that stuff. But there are also interesting states that are not in the Laughlin series, that, like this state that occurs at 5/2 filling. And the thing that distinguishes here, we see full quantization at very low magnetic field, is the appearance of an even denominator fraction. That means something else is going on, and that's the putative non-abelian state at 5/2 that we're still interested in exploring. So if I take you a little further along this journey in development of materials and theory, in a modern sample you can get very good quantization at 5/2, where you have a full 0. I mean, this is a fully gap state. You can see it in detail here. The prevailing theory is that the Ising anyons exist at 5/2, but there are some even more exotic states that may or may not, and there's no conclusive proof one way or the other, say at 12/5, where they may have even more exotic quasi-particles and statistic Fibonacci anyons and all sorts of crazy stuff. But the point here is that as material have improved over time, so is our ability to look at some of these states and resolve them. But everything I'm doing here is still a bulk transport measurement. It's basically hooking up some leads to a square or a rectangle and trying to figure out the fundamental quantum numbers by looking at these bulk transport properties. And that's not always enough, as I'll try to explain. Okay, so, but hopefully at this early stage of the talk, everyone is convinced that the excitations of the fractional quantum Hall effect, or at least should be anyons with fractional charge and statistics. And the bulk transport measurements I just described are shown in cartoon form here, pretty straightforward, pretty simple. But what about these, fractional charge and fractional statistics? Well, the charge for the primary Laughlin state at nu equals 1/3, the first one discovered, was supposed to be E over 3, and that was predicted in 1983. But it took about 15 years of experimental development in quantum shot noise experiments and materials and devices before two groups, one at the Weizmann Institute, led by Marty Heiblum, and another at Saclay in France, demonstrated using quantum shot noise that indeed the charge is fractionalized to 1/3 of the bare electron charge. And that was a 15-year development. Now, as I said, the anyonic braiding statistics are well known to theorists back in the mid-'80s, but I'm giving you a talk in 2025, and that must have taken a while too. So it's only in the last few years that we've actually been able to probe this property more directly. And that's the story that I want to tell you. And what I hope is interesting to students is why it was difficult and what the solutions were. And you can take from that what you will, but one of the statements I'm going to make is, at the end of the day, materials are really important. Making progress with materials, both in terms of making better, cleaner materials, that's one thing, but also in materials design, really is what enabled us to move forward. And sort of that integration of materials, devices, and measurement and closing that loop is super important for making progress. And hopefully that will be something that becomes clear as we go along. So just to be sort of cartoonish about this, what I mean by these fractional statistics, if I have a localized quasi-particle and then I take it around another localized quasi-particle and bring the system back to itself, you say that's nothing, I should be back at the same state. Well, for these fractional quantum Hall states, I actually build up a non-trivial phase. And the question is, how do I actually access that, or how do I measure that directly? Okay? And so what I want to pose, perhaps provocatively, maybe get some response, is that we need a device. We need a device, and we need a device model. We need to understand how our device works, and then we have to have a working model of its operation, the coupling constants, how that happens. And I spent 10 years at Bell Labs, so I can't help but show gratuitously the picture of the transistor from 1947. And this is at a primitive stage. It's a primitive electronic device that we apply voltages. We controllably dictate the flow of current, electrons in this case. What we need is something like an anion transistor, or for correlated states. Do we have the capability of building devices that allow us to manipulate and probe these exotic quasi-particles in a way that the transistor did for electrons? And I think the answer is we're getting pretty close. And here's the blueprint. So in 1997, another one of your famous professors, or would be one of your famous professors, Steve Kittleson, Sivaji Sandhi, Zhao Gangwen, or the senior people, Claudia Shimon was a graduate student at MIT, basically laid out the blueprint of how one might do this. And I believe Steve had been thinking about this throughout the 80s, but this was sort of the culmination. They proposed a device architecture, what we now call the electronic Fabry-Pérot interferometer. And they made some pretty bold statements. We proposed a device, 2 Hall bar, 2 weak barriers, blah, 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 but that will expose interference effects in a strongly correlated system. We show how this device provides a means of measuring the fractional charge, the fractional statistics, and distinguishing between Fermi liquid behavior and Luttinger liquid behavior. So what I failed to mention is, in addition to the bulk properties that are interesting in the fractional quantum Hall effect, for all these topological phases, there's something interesting happens at the boundaries. And what happens that's interesting at the boundaries is that there are circulating one-dimensional modes around the fractional quantum Hall effect bulk states, described by what we think, or Zhao Gangwen told us, are chiral Luttinger liquids, very non-Fermi liquid-like behavior. And I didn't appreciate it at the time. I'm still reading this paper, but this is a blueprint for basically categorizing the topological order responsible for quantization. If you can nail down 3 things, the effective charge, the statistical angle, and something called the scaling dimension, or the tunneling exponent that describes the power that goes into the electron propagator, you can say what universality class the states are that are responsible for this bulk quantization. And so this was the model. Now, this was 1997, and it still took a while. So why did it take a while? I'm going to tell you. That's the only thing I contributed to. So how does an electron Fabry-Pérot interferometer work? Well, we're using the analogy of optics. And you're going to bear with me for a minute and assume electrons don't experience the Coulomb force and they're photons. We define an interferometer. And in the quantum Hall regime, the current is carried by these chiral edge modes. And we define the interference chamber by using these surface gates, these yellow lines. Here's a source contact, here's a drain contact. And the blue region, just considered to be the two-dimensional electron gas. These gates define my interference chamber. And I'm going to use these surface gates to define the electron interference path. These quantum point contacts, these little pinchers that come in here, that's where I partition off these edge states. So edge state comes in, and by tuning this QPC, I partition some of the current, so it backscatters to the other edge. Most of the current goes into the interference chamber and circulates around. Now this has to be coherent transport, so I'm assuming I have coherent transport in here. I partition a little bit more of the current off, and that backscattered current has to interfere with the current that was backscattered at the first QPC. And therefore the current, or the conductance, the current that ends up at the drain, depends on this coherent interference. So the current depends on some basically transmission matrix element squared, basically how transmitting I make these QPCs, and that's fixed. But it also has this interference term, cosine theta. Now that theta is not the statistical angle, it's just the interference angle. I can be dealing with simple electrons here. And we're in a magnetic field, remember. So if an electron traverses a magnetic field, it's in a vector potential, it's going to pick up a phase factor, the Aronoff-Bohm phase. So if I'm considering just non-interacting electrons here, that phase that develops between these two interfering paths is nothing but A, the area, times B, the magnetic field that's penetrating, and is periodic in the magnetic flux quantum, which is just the two fundamental constants H over E. And if I'm dealing with non-interacting electrons, that's pretty much it. I get the AB phase. But what I'll see is an oscillatory behavior in my conductance. So I can measure interference by measuring electrical conductance across the device. And I operate the device by changing its area. These two T gates, those yellow gates, think of the arms of an accordion. I squeeze or expand to make the area bigger or smaller. Or I can change the magnetic field and to change the flux. And just simple single particle quantum mechanics will tell you that if I look for lines of constant phase or constant conductance in a two-dimensional plot of magnetic field versus gate voltage, I should see something like this. These barbershop pole lines are constant phase or constant conductance, and they will oscillate given this Aronoff, the buildup of the Aronoff-Bohm phase. So if I'm dealing with just electrons, that's all I have. But things become interesting if I now project onto fractional quantum Hall states. I have fractional charge and fractional statistics. So this fundamental form gets modified in two very important ways. This periodicity, this AB phase, gets scaled by the charge. So instead of having a periodicity associated with electrons, if I truly have Laplacian quasiparticles with E over 3, the periodicity at 1/3 will be 3 times what it was at nu equals 1. So I can use this as a chargeometer. I can measure the charge. Also, I can see that the interference phase is sensitive to the number of localized quasiparticles. This little spiral in here is a cartoon representation of a localized quasiparticle, the number, and the anyonic phase itself. So by measuring interference, I should have sensitivity to charge and anyonic phase. And so this is what was laid out in the paper by Steve and co-workers. And there's been a lot of elaboration on the details. The details tend to actually turn out to be complicated and interesting. So there's been a lot of other contributors, Bert Halpern, Adi Stern, others. But that's the basic idea. So what's the problem? Why am I giving you a talk on this now? Why wasn't it done a long time ago? Well, here's what you expect. And here's what you really get. If you take a standard gallium arsenide heterostructure or a 2D material or something like that, you get something that looks like an interference. It's not actually interference, but the slope is the wrong way. It's behaving in just sort of diametrically opposite what you expect. And what we haven't accounted for is that these particles are charged. They're not photons. They're not, acting in an interferometer and not sensitive to each other. And so this little interferometer I built is not that different from what's known as a quantum dot. The scale is submicron, and so there, if I create a localized charge excitation here, the Gappel's edge mode can feel it and they interact. And this hadn't been accounted for. And so what actually happens is that there's a bulk edge interaction. This is a dynamical system, and the energy is minimized by not having a constant area, but the overall electrostatic area, the thing breathes. And so this bulk edge interaction causes the area to change with magnetic field. So you can't change area and magnetic field independently. You increase the you increase the magnetic field, you think, I increase the flux. The flux actually goes down because this system contracts to minimize electrostatic energy. Why do we care? This makes braiding unobservable. So in the limit of strong interactions, it fundamentally washes out any contribution from these anyons. So that was a big problem, and it took many years to figure it out. So there's been elaborations on the theory, and I don't want to dwell on that because it's not too important, but there's been a number of theorists over the years who have worked on this, and depending on the strengths of these coupling constants, this is why we need a device and a device model, and we need to be able to, say, in operando, measure those coupling constants. You can get pretty much any interference pattern you want. And I mean, that's an exaggeration, but the regime of operation depends on some coupling constant ratios. And one of them is this bulk edge interaction, which we call KIL. And it parameterizes the energy cost to add, when I create a charge in the bulk, how much do I need to move the edge in order to minimize the charge, minimize the energy. And then there's basically an edge stiffness. How much does it cost to add charge to that edge that is propagating around? And the balance of those parameters turns out to be pretty tricky. Okay? So now here comes the solution. It didn't happen overnight. It took many years. And the work we did was built on experiments done by a lot of other groups and very good experimentalists and making progress, and we just learned from them. One of those is someone who has been a faculty member here in the past, Charlie Marcus. He was a former Stanford faculty. But more importantly, in 1992, he was a non-resident tutor at Winthrop House. So he was also at Winthrop House at that time. And Charlie and I have been friends and collaborators for the last 15 years. But what Charlie did, this is back in 2009, he built two devices. One that has an area of about 2 microns squared, but which is relatively small. And he put a gate on top. Now this big global gate has, it can homogenize the density, but can also act to screen these Coulomb potentials. Remember, I'm arguing that the interaction is obscuring some of the physics. And he did that for two different devices. For the small one, he was always in this Coulomb-dominated regime, no matter what he did. So that was no good. You see these Coulomb-dominated oscillations, and they're not going to be able to operate in the fractional regime, and you're not going to be able to look at anyons. But he did something else, which was a good idea and led us to, I think, a better idea. He made a big device. He has this gate, and he's trying to screen out the long-range part of the Coulomb interaction to reduce these charging effects. But he also made it bigger, so the charging energy, that quantum dot, is reduced. Okay? So he made progress here. This is a huge device by mesoscopic standards, 18 microns squared, and he was able to get what we see is the AB pattern, the classic AB pattern of interference. So that was great. That's really good progress. The problem was this is only at very low magnetic field. It's like half a Tesla here. If you converted that to filling factor, it's like nu equals 22, nu equals 25, far away from the regime we want to operate. The reason he had problems is as you go to higher and higher magnetic field, the coherence of these edge modes is degraded. Basically, you lose the velocity goes down as the magnetic field goes up. So it would work in this very low field regime, but he'd lose visibility of these coherent oscillations as he went up in magnetic field. So to summarize the challenges, there are Coulomb effects that obscure this underlying anyonic physics we're interested in, and that's the physics of mesoscopic charge transport and quantum dots. So if you build a small interferometer, that's good because you have high coherence. You don't have to propagate along the edge so much. But you're in the Coulomb-dominated regime because it's a little object, and to put charge on costs energy. You build a large interferometer, that's good because it reduces the charging energy, but you have low coherence because it has a long path length. So this is where we came in, and when I moved from Bell Labs to Purdue, I had this idea that, well, I want to be vertically integrated. I want to be able to make the materials by MBE, make the devices in the clean room, and then measure them. And this has turned out to be, it took a long time, but also important. And the advance really was building on the advances of others who came before us, but really in the materials. So, and what really matters is being able to close this loop, like iterate, make the device, grow it, what you want, and measure it. And that's proven to be a key in sort of what I do. So Charlie had this good idea, put a gate on top to screen it, but I have this MBE. So I can build gates in, not Bill Gates, I didn't put Bill Gates in there, I put gates into the header structure itself. So the middle 30 nanometer quantum well is where my 2D gap, is going to reside, that I'm interested in measuring the transport properties of. But within the header structure, I put two ancillary quantum wells, these blue regions, 25 nanometers above and below the principal quantum well. Okay, so basically I grew in situ a parallel plate capacitor. Now that makes the band structure complicated. This is the band structure in the growth direction. The blue lines correspond to the electron density. I'm interested in probing the transport properties of this electron gas 1 times 10^11, but it's in very close proximity to these two high density electron gases 25 nanometers away. It makes my device fabrication and design more complicated, but that's a small price to pay for the benefit of screening out these charging effects and getting sharp confinement at the edge. And even after we go to a very complicated device layout, we can still maintain decent quality. So a fully fabricated device is around 10 million for people who care about such things, meaning it's not, we haven't really lost too much by going to this design, and we've gained a lot of functionality. So the device is a little complicated. I have 3 quantum wells, 3 electron layers, and I can't individually contact them, and they're in close proximity. This is not dissimilar to what the 2D material people do now. If you have a layer of graphene and thin layer of 25 nanometers of boron nitride, and then you have a gate on top, it's very much like that, but I've grown it in the header structure, and I have to figure out a way to measure the transport in the middle one without being shorted by the other guys. And so we make contact to all 3 layers, but then we use gates on both the lower and top of the device. You see, looks like the subway system in Boston. You have the orange line here, the red line, the blue line. And we use those gates to selectively allow charge to go to the ohmic contacts or not. And so what I can do by applying local potentials is disconnect the top screening well and then the bottom screening well while maintaining galvanic connection to the middle well. Now my little interferometer is a tiny little mesoscopic device here, well away from all this gating. And so in that region there's still 3 layers, but the transport only takes place through the middle quantum well. And this is a technique I wholeheartedly stole from Jim Eisenstein, who used it in the early 90s for a different purpose. He was studying correlated bilayers when you're really interested in 2 different electron layers and they're strongly interacting. We just used it and applied it to a mesoscopic device in 3 layers, but it works like a charm. So once you do that, we are able to do 2 things. We're able to make very small interferometers. Why is that good? Well, they're high coherence and easy to see effects. I can make a Aronoff-Bohm interference pattern in a device that's 20 times smaller than the one Charlie was looking at. The interference is robust, it's large amplitude, and in this game, surviving to a couple hundred millikelvin is really good. So here's an example of AB oscillations. This is just at nu equals 1. This is an integer state. This is in 2019. But you see high visibility oscillations at an integer state up at high field, and you can see the scale bar here. It's much smaller than anything that had been made previously, yet it's not dominated by Coulomb charging effects. Why? Because these 2 screening layers suppress the long range part of that interaction, leaving behind the physics that I'm interested in. And then we can operate it as an interferometer. You say, okay, great, that's integer, boring electrons. What happens if you go to the fractional regime? So here's the first data. This is now what we do is we turn up the magnetic field to a higher value of magnetic field. So we're at filling factor 1/3. And I see primarily the lines of constant phase, excuse me, with negative slope, as I expect for AB oscillations. But then you see these junk. You may say, that's noise. Look at that. You just have charge noise or there's crap in your system. Well, it turns out it's not. And remember the formula that I showed you earlier for what the interference phase should look like when I'm in the fractional regime. I should see a change in the periodicity associated with the fractional charge, a factor of 3 compared to what the period was at nu equals 1. And if I add or remove a quasi-particle, I should see a glitch. I should see a discrete jump in the phase. Obviously, I can only add quasi-particles discretely. And so I add one or I remove one, and that's going to be associated with a discontinuous change in phase. Now, the period, you're going to have to take my word for it, you can read about it, but both the periodicity in magnetic field and in gate voltage are consistent with charge E/3. We already know that the change in periodicity tells us that the charges that are being interfered here are fractionally charged quasiparticles. And that on itself is not so interesting. It's done in 97 by shot noise, but it's done by a different method here. But then we can go and look at these glitches and analyze them. And what we find out is we analyze the phase on both sides of the glitch, and where these occur in magnetic field and gate voltage is well-defined and known, is reproducible. And the change in phase across these glitches, lo and behold, turns out to be close, divided by 2 pi, 1/3. And this is reproducible. You can sweep back and forth and all kinds of things. And you see, and it gets better with time, but this is the first data. This data, these phase slips, turn out experimentally to be consistent with the removal of a quasi-particle. And the phase slip we see happens to agree with the theoretically predicted anion phase of 2 pi over 3. So this we took as evidence that we were actually using the interferometer as designed originally in the work of Steve and others, and observing this anionic phase. And the real, what allowed progress here was actually just changing the material stack. We had to build a more complicated interferometer, but that's not a big deal. And by designing the materials and the device to sort of a model, we were able to get into the regime where the physics is manifest, where it hadn't been before. So, we didn't stop there. We said, okay, this is a device model. Can I actually change the parameters in a controllable way and to either sharpen the effect or modify it in such a way? And that's turned out to work really well too. You saw some of those early data where the phase slips look a little soft. And well, what we had done in that particular device in design is we'd overcooked it. We had quenched the Coulomb interaction so much that we essentially made the barrier to creating a quasi-particle a little too low. What we did then is say, okay, if this really works, we can go back and design a new heterostructure and a new device geometry to accentuate other parts of the physics. And we made a smaller device on a lower density sample. And here's a zoom in. This is a subsequent publication where these phase slips are, sharp as can be. They're really discrete. This is the data. And that was through design. You also see different regions of operation. This is in what's called an incompressible region, where we're only introducing, on rare occasions, a quasi-particle. But if I go out into the flanks, if I extend the range over which I operate this device to where essentially the fractional quantum Hall effect is breaking down, there's a finite range in magnetic field. You go out into the flanks, you transition to a region that's where it's called compressible, where the energy to create quasiparticles is, the distance from the chemical potential is not high, and so you readily make quasiparticles. And this transition you see corresponds to a change in periodicity from 3 phi naught periodicity to phi naught periodicity. And that is a prediction of the theory as well. And it was only in these subsequent iterations of device design and heterostructure design where that became really clear. Now there's a penalty to be paid. I introduced a little bit more Coulomb interaction. So that means the interference phase, or phase slip I measure, will be slightly off from the pure anionic phase. But I'm not going to have time to go through it in this presentation, but these coupling parameters, it turns out, can be measured in situ, or in operando. I can characterize the device and the coupling constants by independent means. And then I can see if those coupling constants that I extract translate into the magnitude of the phase slips we see. And so, again, this is all buried in the theory. I don't want to go into the details, but the anionic phase, the fundamental phase of the anyons, of course, is invariant. It doesn't depend on the device. But the phase that I actually extract in the measurement depends on these coupling parameters that I can measure by doing differential conductance measurements, operating as a quantum dot. It's all details of quantum mesoscopic physics that David and others and Cam all know about, but you can extract those parameters in situ. And then you can say, well, if I measure those parameters, does the angle of the phase slip I measure comport with the anionic phase? And it turns out it does. And so we are able to reconcile the phase slip measured here with the anionic phase, which again is still 2 pi over 3 for 1/3. And it shows us now that we have a device in which we understand and can control. And then you can hope to manipulate things when you move from a discovery to, okay, I think I can control this thing and do more with it. So the phase slips become very sharp. There's a clear transition between different regions. And so it's holding together. Now, I'm not going to go, let's see where I am. Oh, I'm already really late. I'm not going to go into all the details, but if you're interested, I'll be around on Thursday, Friday. We can talk about, you can extract all these parameters by various measurements. And what's nice now is we have a working model provided by the theorists, and we can we can measure and then feed into this all the parameters of interest. Now I'm just going to rush through this because you may say, well, okay, good. You got lucky at 1/3. Can you extend it to more complicated fractions, say ones with multiple edge modes, the hierarchy states, or these potentially non-abelian states? And I think the answer is it seems that we can. So can we go to more complex fractions with smaller gaps or different edge modes? More recently, we did it at 2/5, one of the principal daughter states coming out of 1/3, where things are more complicated. The charge is reduced to 1/5. The anionic angle is minus 4 pi over 5. It's not just measuring the filling factor anymore. And there's reasons to worry about this. Bert Halperin and Dima Feldman told us it was going to be hard. No kidding. But there are physical reasons for this. There's a smaller gap, multiple edge modes, small effective charge. But anyway, this has worked out, and we measured interference at 2/5, and we can selectively partition the different edge modes and interfere them independently, extracting the effective charge and the statistical angle. And that took a little bit of a redesign of the header structure and the device. It's not super important, but you have to go back and redesign it so that you have the necessarily visibility at a particular fraction. And that seems to be working. And so now the goal is, okay, we've done it for abelian cases. And can you extend this to non-abelian states? That's what we're working on right now. And can you use this simple device architecture to fully parameterize the topological order in one of these states? It doesn't need to be a fractional clump Hall state. It could be a fractional Chern insulator. And it seems the answer, if I'm optimistic, is yes. If you come to Thursday's talk, I'll tell you why we're able to measure this scaling dimension or the tunneling exponent as well. But you know, there are details in here. Moving from 1/3 to 2/5, much more fragile state. Here's the quantization at 2/5. The red trace corresponds to the quantization within a device. Much smaller gap. The region of interest is much narrower. But we have these QPCs, these little deflectors that we use for partitioning off the edge modes, and they are reproducible, and we can scatter either the inner mode or the outer mode, and that's worked well. I will just rush through this to get to the conclusions. And my outlook on this is that you know, as you go to more fragile states and more complexity, things obviously get harder, but it works. And hopefully it'll be working for not just in fractional quantum Hall physics, but for other systems as well. We can analyze the periodicity of these oscillations at 2/5, gives us the right charge and the right statistics. So let me jump to the conclusion. I know that was a little rushed at the end, but hopefully you got the message. So Fabry-Pérot interferometry may be used to quantitatively determine anion statistics, fractional charge, and probe chiral Luttinger liquid behavior at the boundaries of fractional quantum Hall physics. That's Thursday's talk, that's a teaser. But using a series of measurements on what I would call these anion transistors, we now have the capability of fully, I think, parameterizing the topological order. And that, I hope, will be really powerful for all these new phases that are being discovered in other material systems. And of course, you know, we want to study non-abelian states. That's the next step for us. And very recently, we've come up with a new header structure design that allows us in this screening well structure. It's a very different one where we have a different type of screening well than we've used in the past, but it allows us to have strong 5-half states existing in this modified 3-layer structure. And I think this certainly will be exciting over the next year or so as we try to make these work. So I'll just leave it there, and thank you for your attention.
Are there questions?
Tunnel coupling of your channel to your embedded screening gates, is that negligible?
Yes.
And is that kind of an issue for the degree of screening you want to get to for the
So the barriers are quite high. There's no direct tunneling. And what does become an issue is that, you know, you're trying to screen out the long-range part of the Coulomb interaction, but you don't want to cut out the short-range part that gives you the fractional quantum Hall effect in the first place. So obviously, there are length scales involved, say the magnetic length at a particular field I'm at for refraction, that I can't be getting these guys closer than the magnetic length, or then I'll screw up and soften the fractional quantum Hall effect itself. So there's a limit, and that becomes more challenging. Why it's been to get to 5/2, the magnetic length is longer. You have to have these screening layers set back a little further, and so there are constraints. You can't put it arbitrarily close because you don't have an arbitrarily high barrier, tunneling barrier. Maybe if you had a monolayer or two of boron nitride, that would work, but not in gallium arsenide. But then there's also the considerations of not softening the short-range part of the Coulomb potential, so I don't kill the fractional effect. So there are bounds on how much we can do, if that's what you're asking.
Yeah. Actually, if I could squeeze that follow-up, and if you play with the density for that length scale, so you screen the long-range part, but the short-range.
Well, yeah, I could, and I could see one way of doing that is seeing a softening of the gap. So I start bringing it close, and I can see the principal gap at 1/3 or 2/5 or something in the principal well at a given density become smaller. And so I have a way, and I can measure that gap while we're doing these measurements. I can see it when I need to worry. And of course, I also have isolated control where there's no screening wells, and I measure the gap there, and I can compare those two. But it is not, it's not, I don't have infinite tunability.
Just following up on this, which I could probably answer if I could do arithmetic, but in units of the distance between electrons, how far is it to the gates, and also how far is it across your device? How big are they in units of the inter-electron separation?
Okay, so depending on, can I use the magnetic length? You mean?
Okay, magnetic length is roughly the same
Yeah.
as the spacing.
So it's, those layers are typically several magnetic lengths away.
Okay.
And that's a boundary that we use where we say, okay, if the magnetic length is going to be 7 nanometers here, I want to be 25, 35. It's from center of well to center of well, so it's actually a little bit more. So that's several magnetic lengths away.
And across the...
Well, the device, electronic length is typically submicron by, so say 800 nanometers by 800 nanometers.
So big.
Yeah, which is what you want.
Yes, yes.
Exactly. I don't want it to be.
No, I was just checking.
So I have a question, just an experimental question. Suppose that you'll go tune to one of these joggy places, tune right onto it.
A joggy place?
The place where
Oh, facelet?
anyonic
Yeah.
occurs. Is it noisy? In
Uh,
other words, does the charge in there?
yeah, because I haven't done that experiment. We can go back and forth over it and it always reproduces, but presumably that's where it's just, if I sat there, it's just energetically favorable to have the quasi-particle state occupied or unoccupied. So I would expect there would be a change. In the time domain, I expect there might be.
The reason I ask is that since it's fractional, it's hard to transport it from the outside to the inside. There's a matrix element issue, and it's not as curious what the time scale is for the charge state to change.
I don't have a good answer for that right now, and
I have a good answer for that.
You didn't do the experiment.
No, but somebody else is going to.
Oh, no. Don't go with Andre. It's a very different answer because it's very, very different energetics and disorder.
Different energetics, but in a different realization of this later, they have seen some of this dynamics, this slow dynamics.
Yeah, and I don't completely understand and the dynamics change from Philip's experiment to Andrea's experiment. The time scales change, and I don't fully understand it. They see, no?
So Philip now understands why they were fast for him, and they're no longer fast for him after he made a modification of adding a radiation shield.
Okay. Oh boy. Yeah. Okay.
Kelvin radiation or something like that, and that was enough.
Yeah, we've shielded ours. I don't see dynamics in the way that they've reported in the graphene structures, but I haven't looked in detail either.
Yeah, I could imagine an experiment where you oscillate. You oscillate with parameters.
Yeah.
And force it to change and see how fast it follows.
It can follow, yeah.
So that's actually, by mistake, what Philip was doing.
I see. So what was the, okay.
By not shielding. I don't know if that's actually true, so, but okay, fine, good. He's improved his low temperature hygiene. But in Andrea's case, things were hysteretic as well, and all that. I can, on a time scale of minutes, sweep back. That was on long, like minute time scale. That's not doing microwave measurements or anything. Sweep back and forth, and I don't see the history. I see reproducibility, it goes back and forth, but I don't see the same time scales that they do. And I think that's the disorder is very different. We have long wavelengths, gradual disorder in gallium arsenide. They probably have less infrequent but deep disorder, and so that can change the time scales. Okay, there's a question there.
So I'm curious about this proposed probe for the non-abelian states, do you need like a different interferometer geometry to be sensitive to like non-conductivity?
No, the signal would be different. Now, the original proposal was to build essentially a qubit, which has two chambers and then antidots in each of the chambers to cycle on and off quasiparticles. But theory that came out of Artie Stern and others, and basically depending on the parity of the two quasiparticles, the interference will turn on and off. So it's a very different signature that you'll see if you have non-abelian quasiparticles and you're flipping the parity. And so you can use the same geometry, just the signatures will be different.
Do you have any control over the parity? Like you're saying, like there's two vortices in there. They can be
Yeah, well, the plan, it's just a plan, is, and there's some evidence that it'll work, not my evidence, but some from the Weitzman, that you can, build an air bridge and have an antidot, a very small gate that serves as a local, a nucleation point for the quasiparticles, and by doing that, you should have some degree of control. Now, it hasn't been done for E/4 quasiparticles at 5 halves, but there is some indication that that can work in interferometry geometry. It's what we're going to try. We're trying to build those right now.
Are there other questions?
I just have a similar question about the device structure. When you have these multiple layers of QDEC and screening layers, how do you actually gate the kind of active layer for the quantum point contacts?
How do you,
How do you gate the middle layer without when you have these?
well, you put, where the interferometer is, of course, you punch through the top screening layer. So there's the screening, say there's the top QDEC, the one you're interested in, and the lower screening one. And the interferometer, of course, there are surface gates. So I have to punch through to locally deplete, and then I can control the density in the primary quantum well. But if you look at the electrostatics, and we've done simulations of this, you're actually just punching through very locally. And it's like you had a stencil or something, and you're shining the flashlight through. And then you're not perturbing the density out in the middle of the region at all. It's very local to the gate. And then you're just shining the flashlight down to the intermediate well. And of course, in gallium arsenide, we have well-defined conductance plateaus. We know what we've done because I can just measure the conductance, and I can see, do I have how many modes I have circulating around and with what transmission. So we're a little bit lucky there in that it's very easy to see what the gate potential has done, because there's just very clear signatures in the transport. And so it's like shining a light through this little stencil.
So let me just repeat that Mike will be here on Thursday and Friday. He's giving a follow-up seminar on Thursday at 3:15 in McCullough. So anyway, let's thank you.